So the second part of the adrenal gland that we're interested in is the adrenal medulla, where the catecholamines come from. The adrenal medulla acts as a postganglionic structure. There's sympathetic preganglionic fibers that run into the adrenal medulla, and when they're stimulated, they release acetylcholine across the synapse onto these chromaffin cells that then degranulate. And when degranulation occurs, they dump their contents into this arterial capillary that runs through the adrenal medulla and then carries off the epinephrine and norepinephrine that exists within these vesicles around the body, promoting a systemic sympathetic response. This is controlled by the sympathetic nervous system and therefore responds to the stimuli that increase sympathetic tone. Now, most of what's held inside these vesicles are an epinephrine, there's 85% epinephrine, and then there's 15% norepinephrine. There are enzymes and other things within the vesicles that aid in its function. And the amount of epinephrine that can be released will increase its concentration in the blood up to 20-fold. Norepinephrine will rise 3 to 4-fold. These hormones are very fast-acting, and they're also removed very quickly as well. They have a potent effect on not just metabolism, but also on other aspects of the body. They increase cardiac output, they vasoconstrict, and therefore their influence is rapidly regulated. So this slide shows you the basic properties. As we know, it comes from the adrenal medulla, from the chromaffin cells, and they're amine hormones that are soluble and carried around the blood, mostly free solution, but some bound to albumin. A stimulus for release is stimulation by sympathetic preganglionic neurons, so a fight or flight mode, and removed by monoamine oxidase as far as epinephrine is concerned, and norepinephrine is removed by catechol O methyltransferase. And like I say, the half-life is very short. The mechanism of action is adrenergic receptor stimulation, and the biological responses are very varied. You would have come across these particularly in the cardiovascular aspect of the course. Here we're talking about metabolism. So what do these actually do to metabolism? Well, they're major substrate mobilizers. They will break triglycerides down into free fatty acids, and then the liver will convert these into keto acids. Glycogen stores will be broken down to glucose, and in the liver released or used in the muscle turned into lactic acid, or depending on the type of exercise, maybe just carbon dioxide and water. So the role of the catecholamines is to get a lot of utilizable substrate out, increase the amount of glucose, increase the amount of keto acids, and it also reinforces the activity of glucagon, which does very similar things, by stimulating its release from pancreatic islets and inhibiting the release of insulin. And so some of the things that will stimulate catecholamine release is like low blood glucose. So that will raise then the blood glucose to counteract this drop. Physical illness or trauma, stresses that will release adrenaline. I mean, these are things you can relate to because we've all been in situations where you feel your nervous energy increase, your excitement increase, stress, you start shaking, and this is because of the release of adrenaline, epinephrine. Hemorrhage, vasoconstriction is a particularly effective way of losing less blood. Exercise then demands energy, so releases epinephrine. Hypoxia, again, it's a stressor, and during stress your body increases the amount of energy it's able to access, and then exposure to cold, and this is to regulate your core temperature. And so all these things show you how the catecholamines generate energy for use in threatening situations.